Hello, everyone. In the last class, we looked at state space representations and standard linear ODEs and input output models, wherein you write down your multiple second order ODEs as one single higher order ODE. In this example, we had two second order ODEs that we then wrote down, eliminating one of those variables, so then have one fourth order ODE. So that can be in the standard linear form or the input output model. And essentially, you are just uh, replacing the first coefficient with 1 to get it in the input output model. Um, so this over here, it would be the standard linear ODE. If I were to divide everything by M1, M2, then I would have it in the input output model. Okay, that's just the standard representations that you have for a single higher order ODE. And then in the state space representation, you essentially have four first order ODEs. How is that the case? Um, in this example here, where you have n different state variables, you now have a first order ODE, x1 dot is equal to something related to x1, x2, and so on. And then you have all your inputs coming into the picture here. So essentially, you're able to write it as x dot is equal to ax plus bu, where this is now a state vector that's differentiated ones. So it's a first order ODE. And you have your system matrix capturing how all your state variables interact with each other, and your input matrix capturing how your input vector affects your state variables. We have a very simple example where it was just one second order ODE, and you now write it here as um, x dot is equal to ax plus bu. And this here is your state matrix. This here is your state vector, which has been differentiated here. B is your input matrix, and U is your input vector. Okay, we'll do some now going forward. Every time that we write down our equations of motion, we'll also write in the state space representation. So today we're going to move on to rigid bodies, wherein previously, when we had particle approximations in our kinetic diagram, we only had to account for the position of the center of mass. Right, so if you have something like this, mx double dot, you're capturing the acceleration, the inertial forces that this body is going to be experiencing. And so the position of the center of mass captures everything essential about the body. When you move to rigid bodies, which are now not just particles, you have to then account for the rotational inertia as well. So never forget there is an inertial force that's coming in due to the motion of your center of mass. So there is your mx double dot. But now the rotational inertia also has to be accounted for. So if theta is accounting for how this body is oriented, let's say initially it was oriented along this axis and then it has rotated, then you have some theta being measured in this way. Then you have j theta double dot or I theta double dot to represent the moment of inertia I or j and the moment that is set up. Okay, so there is a moment that is being set up, and so in addition to the position of the center of mass, the rotational inertia must also be accounted for. So what does this look like? Every time that you are drawing your free body diagram, you just account for whatever's provided, whether it's including the torques and moments and the forces and so on. But when you're doing the inertial diagram, that's the kinetic diagram, you will have from your center of mass some mx double dot and then some moment related to the rotational inertia. That'll be j theta double dot. In this class, I will always provide you what is the value of j, and it'll be about the center of mass because that's usually how it's given. About the center of mass, about the axis of rotation. Okay. Just to clarify, when we looked at these torsional systems, the reason why we didn't account for the motion of the center of mass is because, uh, by definition, the center of these disks are held fixed. And there's only the twist that you're modeling, which is why you didn't have that mx double dot here. But then there was a rotational inertia giving you j1 theta 1 double dot and j2 theta 2 double dot. As you can see, that didn't exist for this mass over here because this is a particle, and so only its position matters. Going back to perhaps this one here. Now, since these are particles, in the kinetic diagram, we never had to account for any rotational component. It was only the position of the center of mass that we were capturing. These are the kinetic diagrams. These are the FPDs. In terms of FPDs, nothing changes. It's just that now we have to account for the rotational component when we have the kinetic diagrams. Okay, so there's one extension. And then another extension is I'm going to include another passive element. So it's an extension to the spring and damper idea, which we had seen in translational and rotation and torsional systems. Now, if we had a torsional spring that is attached to some rigid bar, perhaps, maybe it looks like this, and its undeflected position was somewhere here as this vertical position. Now, if this bar has been rotated from the original position by theta, then this torsional spring will exert a restoring torque of, if it has a torsional spring constant of kt, then a restoring torque of kt times theta will be applied to whatever object is attached to. Okay. Um, so if this here is a rigid bar and it has been deflected by theta from the undeflected or the natural position of the torsional spring, then the torsional spring will create a restoring force, a restoring torque. Well, the rigid bar will experience a restoring torque, which is given by tau s is equal to kt times theta. And if instead of a torsional spring, it was a torsional damper, let's say, so that would be shown with this cylindrical mass attached here. In this case, this here is theta, so theta dot is also to the right, positive to the right. Then tau d would be equal to ct theta dot, where ct is the torsional damping coefficient. Can you tell me what are the units of these? No, of course, there's a recorded video, so that doesn't work. But there's the torsional stiffness constant, which would be in Newton meters per radians. And this one here is the torsional damping coefficient, which would be in Newton meters seconds per radians. Okay, so So these are the new concepts. Um, a lot of times when you're analyzing a system, some physical law or some property will be provided to you, and then you make use of that to then define a model for that system, which in this case is the equation of motion that we're developing. Let's do this with an example first. So here is the problem. You have a uniform bar given to be of mass m and length L, has a moment of inertia Ig of ml square by 12 about its center of mass G. So it means that your rotational moment of inertia is ml square by 12 when the rotation is happening in this axis, that is outward from this plane. There's a point mass m that's rigidly attached to the bar, which means that this mass m is something like it's welded to this point here. So there is a rigid bar, and then on one end you have particle mass m that is rigidly attached. So first, what is the degree of freedom of this system? Since this mass m cannot move relative to this bar here, if you have just theta, you can fully define what is the uh, position or the state of the system. Um, the hinged end of the bar has an attached torsional spring of stiffness kT. So you have this end here with a torsional spring that's been attached. So if it moves from its vertical position, um, it's understood that the undeflected position is when it is vertical. So as it is moved by theta, then this bar is going to experience a restoring moment of kT times theta. The other end is attached to a spring. So this end is attached to a spring, the other end is fixed to a wall. And the center of mass, that is at this position L by 2 that is marked, is attached to a damper of coefficient C. Okay, so this is a bit of an extension from what we've been studying. Um, so this is a guided example. Essentially, there is a 1 degree of freedom system where theta fully describes the system position. You'd have theta dot for its velocity. Let's now do the kinetic diagrams first. So this here is the uniform bar, and then we have that mass m. Okay, so let's start with the mass m. What is the acceleration that this mass m would be experiencing? The acceleration of this mass m is related to the rotational motion about this axis, right? So in that rotational motion, you have two forms of acceleration. One is the centripetal acceleration, and one is a tangential acceleration. Try to recall what these are. The centripetal acceleration that's pointing to the center will be m. I'm going to draw that in red actually. It will be so here you have m l theta dot squared, right? It's r omega squared. And then the tangential one will be m l theta double dot. There's no rotational inertia for this because there's a particle. This here, on the other hand, its center of mass will be experiencing an acceleration that is again towards the center, that is centripetal, and one that is tangential. This will be given by m l by 2 theta double dot. Why is it l by 2? The radial length from this point here is l by 2. So this is mr theta double dot, and then here you have m l by 2 theta dot squared. This here is a rigid body, however, which means that you do have to account for its rotational inertia. And so you have to draw it in the direction of increasing theta, which is in this direction. You're measuring from this undeflected position as theta here. And so you now have a rotational inertia component of creating a moment of ig theta double dot squared. It's just ig theta double dot. So j, the moment of inertia, theta double dot. In this case, the moment of inertia is given as ig. So this is m L squared by 12 theta double dot. That's a moment, which means that I can draw that anywhere on this body. It can be here, it can be here. I'm just drawing it here so that I have space. Because the next thing I'm going to do is that these two bodies don't need to be considered as two separate bodies since they're rigidly attached, which means that I could draw this as one single body here because it's just a 1 degree of freedom system. Okay, so I hope this makes sense. So this here is a kinetic diagram. Let's then try to draw the free body diagram. So I'm drawing the same component again. This here is the object that is rotating. What are the forces that it's experiencing? First, do you have to account for gravity? Well, this spring is oriented horizontal. So starting from this position, it would be horizontal, and then as it moves down, we assume that it still remains horizontal. But it's not along the direction of gravity. And so that means that the static deflection in this spring will not be counteracting gravity, which means then that the gravitational force will exist. So you do have to draw mg here. And don't forget, there's another mg here. Essentially, having this system where you have one particle that is attached rigidly at some other point, it creates this distribution of mass, wherein this here is a uniform bar of mass m, and this here is another mass that's attached. Okay, so they're both of the same mass m, which is why it's mg. Okay, that's one thing out of the way. We just defined this idea of a torsional spring, and so when you have theta angular displacement from its natural position, you will have a moment that's given by kt theta, that is tau s. What are the other components that are going to be acting on this? So as this rigid bar, it rotates over here, how much would be the deflection in this spring? So if you were to look at the rotation here, this is an arc that is set up wherein you have a radial length of L and the rotation is theta, which means that this arc length is L theta. So your spring from its natural position that is over here is being deflected by L theta, and you can see that it's going to be in compression. So spring Fs will be in compression for positive theta. um, with the value. Yes, I'm going to do it this way. Okay, compression with Fs is equal to K times the deflection, which is that arc length. Now, why am I saying that that arc length is the same as a deflection here? Um, that's because we assume that the spring remains horizontal and that this is a very small amount of deflection. So that's how it becomes K L theta. The L theta is a deflection. And the damper has a force Fd, which is going to be related to the speed of this point here. So this moves over an arc length of L by 2 theta. And if I were to differentiate that, then this would give me L by 2 theta dot. So that is the speed of this point. In this case, it is going outward. So this would be in tension with Fd is equal to C L by 2 theta dot. You could draw the individual free bodies for the damper. So this damper would be in tension and the resulting reaction would be to the left. So I'm going to directly draw that here. You have here CL by 2 theta dot. And this spring is in tension and the reaction would be in this direction. So I have another force here, which is Fs being KL theta. Are there any other forces? You do have reaction forces at the pin. You should not forget that. So this here is, let's say, the component of the reaction force that is vertical, that is Ry, and this here is Rx. Did we capture everything? Let's just go over it. So this here is one rigid body. As it moves by theta, angular deflection, this will create a restoring torque. We captured that. This damper will have experienced a speed that is defined as L by 2 theta dot and creates a restoring force to bring it back. Well, not to bring it back into the position, but to resist that velocity. This end would have compressed the spring by L theta, and so this will create a restoring force of K L theta. We have to account for the gravitational forces because the spring is not holding any static deflection to counteract that gravitational force. Okay, with that, we have everything that we need in the free body diagram and the kinetic diagram. Now, you're free to apply Newton's second law. So you can do sigma, the sum of forces in the free body diagram is equal to the sum of forces in the kinetic diagram. The problem is that you will have to then account for the reaction forces here. If that is important to you, you will have to go about doing that Newton's second law. But instead of that, we could take moments about some point. For example, if you take the moment about this point, then both these unknown reaction forces, they will vanish because they have zero moment arm length. And for that reason, taking the moment about this hinge point is usually beneficial. That's what we're going to do. So we have the sum of moments in the free body diagram about point O, let's say that's the hinge point, is equal to the sum of moments in the kinetic diagram about the same point O. When you take a moment, you do have to account for which point you're taking it about, and it has to be the same on the left and the right. We can define a certain direction to be positive. Let's say that the counterclockwise direction is positive. So now all you have to do is take the moment about this. Oh, I did forget something. I forgot that there's an external torque. It's an oversight. This here is tau of t. What's an external torque? Okay, so immediately, since we're taking moments, you can write down the existing torques or moments as you have kt theta in the same positive direction. So you have kt theta minus tau of t, because they're already defined as moments. Now you have to look at the forces. So here, this is a force. Its line of action is at a distance of this much away. So if I were to now define the angles, you have angle theta here, which means that this angle is also theta. We have this length of L by 2. What we're looking for is a moment arm length, which is this length here, to the line of action of force. So this is L by 2. This theta means this is L by 2 sine theta. So you have L by 2 sine theta times the force of mg. In what direction is that? It is in this direction, so it's r cross f. You could do that with the right hand rule. You go in the direction of the position vector and then you cross it with the force vector. In the right hand rule, you would have your fingers, the non-thumb fingers, curling in that rotational direction, and you will have that it is pointing inwards, which is opposed to this direction. So you have a minus L by 2 mg sine theta. Then you have this force here. So it's L by 2. You're looking for this distance because that is the perpendicular to the line of action of force. So L by 2 cos theta gives you that. So you have L by 2 cos theta times the force of CL by 2 theta dot. Okay, now is it positive or negative? So you have R cross F. This is in the same direction as what you defined as positive. So you have plus over there. And then you have this gravitational force setting up a moment about the point O, which is going to be at a distance of L. So there's the line of action force. You're looking for this distance. This is L sine theta. Is it positive or negative? It is going into the plane, which is opposite of what we define as positive. This is minus. What else do we have? We have this force here. So this is KL theta, line of action of force, perpendicular to that. So this is L cos theta. So you have L cos theta. Is it positive or negative? Is R cross F. It is in the same direction, so you have positive. And so you have L cos theta times KL theta. So these are all of the moments in the free body diagram. Be very careful in how you define positive and negative. What is the moment arm length? What is the force? And so on and so forth. All of this is equal to, now on the right hand side, you have the kinetic diagram. You're again taking the moment about O. So you have this moment m L square by 12 theta double dot, which is opposed to this direction. So it's minus ml square by 12 theta double dot. There are no other moments, so now we have to look at the forces. This force here has zero momentum length because it is collinear. There's no perpendicular distance to this force here or this force here. So then we have to account for this one, which is at a distance of L by 2 away. So it's L by 2 times ml by 2 theta double dot, which means there's r cross f. That's what we did just now. What direction is that? It's in this direction, which is opposed. So again, minus. And then finally you have this here, L times ml. So L ml theta double dot. And this is again r cross f, giving you this sense, which is opposed to this. So you have minus. Just be very careful when you're writing this down. Breaking it down into these kind of steps helps you. Always keep checking back in this figure if you've captured everything. So right now we have applied the moments about the same point O to then arrive at this relation here. If you were to now carefully reorganize this, you will get 4 by 3 ml square theta double dot plus cl square by 4 cos theta theta dot plus kl square cos theta theta plus kt theta minus 3 by 2 mgl sine theta is equal to tau of t. This here is your equation of motion, but you can see that this equation is only really accurate for very small theta because we have already made an assumption where this, we're keeping this spring to be horizontal and this to be horizontal as well. That's how these forces are in this direction. And so we've already made an assumption that this theta over here is small. And not only that, this is not a linear ODE. So a linear ODE must be able to fit this representation where you have some constant times your variable differentiated how many ever times, another constant differentiated again a fewer number of times, and so on. There's no cos of your y or a sine of your y, so it's not in the linear form. And when your angle theta is really small, it is possible for you to make the small angle approximation, which basically has that cos theta is approximately equal to 1 for really small theta, and sine theta is approximately equal to theta for really small theta. Okay, why is that? You could use the Taylor series, which we will look into in future in when we do linearization, which is an important component of this course. But for really small theta, let's see what really happens. So you're looking at this here is your really small theta. Okay, so this is theta that's really small. There's some L hypotenuse. What would this here be? That would be L sine theta. And what would this here be? That would be L cos theta. Right? This is very familiar. Now, why is L cos theta approximately equal to 1? That's because this L is going to be really close to this L cos theta. Right? If you had this theta becoming smaller and smaller and smaller, you can see that they almost overlap. So for sufficiently small, they would be overlapping, which gives me L cos theta is equal to L. And for non-zero L, you will get that L cancels out when you divide by L, and you have cos theta equal to 1 for really small theta. Okay, that's just me explaining in a really simple way. What about L sine theta? Is it 0? Well, it would be a better approximation to say that it is theta. And the reason is that if you were to think of this as an arc in a circle, this here is L, this here is L. Um, oh, okay, I'm going to draw that separately. So you have a circle with a really small angle subtended theta. This is the radii L. What is the arc length here? This arc length would be L theta, right? And this L theta for really small theta would be very similar to this distance here. So it's like you would have, if I were to zoom it in, I'd have this as my L sine theta and this as my L theta. I hope that makes sense. There's a circle radius. You have theta subtending an arc of L theta. To look at this segment would be L sine theta, as we just defined. So L sine theta would be approximately L theta, and for non-zero L, you essentially have that sine theta is approximately theta. Okay, this is a really simplified explanation with Taylor series expansions, which we'll look at more closely later. You will have this more concretely defined. I'm going to write this equal to 1 or approximately 1 for small theta, and sine theta is approximately theta for small theta. This is the small angle approximation. It's basically that for small theta, cos theta is approximately 1 and sine theta is approximately theta. Okay, so this allows us to now write down the equation of motion as 4 by 3 ml squared theta double dot plus cl squared by 4 theta dot plus you then obtain kl squared plus kt minus 3 by 2 mgl theta is equal to tau of t. This now is in the linear ODE form, which means this here is your first coefficient, that is a2 of t, which happens to be a constant that's not changing with time. This here is a1 of t, and this here is a0. And that variable theta double dot is essentially y double dot. This here is y dash, and this here is y. This is your input u. Okay, so I've now written it in the standard linear ODE form, which is what we have defined over here. So now n is equal to 2 because second order. It's not a constant anymore. It's not a variable coefficient anymore. It's a number. So there's no an of t. It's just an. There's an minus 1 and so on. On the right hand side, we have just this u. We don't really have any coefficient in front of that. That's how this is the standard linear ODE form. If I had to write it in the input output form, I would divide everything by 4 by 3 ml square. So then I would get theta double dot plus 3 by 4 ml square times cl square by 4 theta dot plus again 3 by 4 ml square times kl square plus kt minus 3 by 2 mgl theta is equal to 3 by 4 ml square tau of t. So this is the standard linear ODE form. This is the input output form. In this case, I would simplify this to be 3c over 16m. And this now matches the input output form where the coefficient here is 1. So this would be that coefficient that we just defined for y dash. And then we have, so that's essentially this here is a coefficient of y dash. This here is a coefficient of y. And now we have a coefficient for the input, this here being u. There's a coefficient of u. Okay, so what about the state space form? Why don't you try it yourself? To be able to write the state space form, we first want to isolate theta double dot. So it would be minus 3c by 16m theta dot minus everything that we have here. And then plus this over here. And we have one state variable as theta dot, which is being differentiated. And then we have, so if I were to write this, I would write it as d dt of theta dot is equal to this. And then d dt of theta is equal to theta dot. Okay, so now I can write my state space representation wherein I have that differentiation theta dot theta. If I write it in this order, then on the right hand side, the state vector has to be in the exact same order. So if theta dot theta plus you have two components to your input matrix, and then you have one tau of t. You now have to fill in the values in these matrices. Try that yourself. First, we can do this one. That is, this here is just saying that the differentiation of the state variable theta is theta dot, which is the other state variable. So I can then write this here as 1 and this here is 0. What about this equation here? You have that this is a coefficient of theta dot. So I have that coming in here. And then I have this as a coefficient for this one. Um, to make it clear, I'm going to draw these guidelines. Okay, and then you have 3 over 4 ml square here. And this equation didn't have any relation with tau of t, so there's 0 there. Okay, so this here is your state vector, that is x. This here is your state matrix A. This here is your input matrix B. This here is your input vector U. And this here is x dot. So in your state space representation, there's a linear state space representation. You have x dot is equal to ax plus bu, and you're done. You can extract some meaningful information from this matrix using its eigenvalues and so on, which we'll get to later when we're analyzing these systems. Right now, we're just developing system models. Okay. I hope this stuff makes sense. We introduced a few new concepts. One, when you have rigid bodies instead of particles, you now have to account for the moment of inertia as well. The moment of inertia in the kinetic diagram, along with the acceleration of the center of mass. Here we have all of the inertia in the system captured in the kinetic diagram. Here, in the free body diagram, the new ideas were related to this torsional spring, which is now going to create a moment that is restoring the rigid body back to its original position. It's now deflected by theta, so it's kt theta as the restoring moment. A revision of something we looked at is that since this spring is it's not vertically oriented, it's not along the direction of gravity, there's no static deflection that's going to counteract gravity. And so you do have to account for gravity in these free body diagrams. Okay. Let's do another problem here. You have a uniform bar of mass m. So this here is a uniform bar of mass m and length L. Given to you is a moment of inertia about its center of mass. It is hinged at O with a torsional damper of Ct and is attached at its center of mass to a vertical spring of stiffness K. Other end is connected to a vertical spring of stiffness K2, and then the other end of this spring is connected to a particle mass M. The system is suspended from the ground by means of another spring K3 and a damper of coefficient C. Obtain the equation of motion for this system when acted upon by this torque tau of t and the force F of t. First, will gravitational forces have to be included in the free body diagram? No, because all of the springs already carry the um, static deflection that's counteracting gravity. And as you can see, all the measurements are from the SEP. If instead the measurements were from the undeflected position, then without question, you will have to include gravitational forces. Okay, so how would you like to do this? If you're unsure that gravitational forces can be neglected, then you first want to draw some undeflected position from which now when gravitational forces act, it'll come down to this SEP. And in doing so, it'll set up a static deflection in this spring, and this spring. The dampers play no role because at the SEP, there is no speed or velocity that is contracting. And then you would find out what is the amount of static force inside these springs, and you will have a relation that shows how the gravitational force mg and mg cancel out. And then when you do the case from the SEP now, with these external forces acting on it, you will find that that relation will allow you to cancel out those the gravitational force terms. Okay, so let's now approach this problem again. I would highly recommend that you pause the video and try solving this yourself. Um, I'm now going to go ahead and then solve the problem. In this case, is it a 2-degree of freedom system or a 1-degree of freedom system? It's easy to see that you have theta and you have y, so it's a 2-degree of freedom system. You need those variables to be able to represent the position. In this case, the particle on the right, if I were to draw the kinetic diagram, the particle on the right will have an inertial force that is along the direction of positive y, so it's my double dot. This rigid bar will have it will have a inertia moment that is in the direction of theta, and I would show that as shown here. You have Ig, which is ml square by 12 theta double dot. Now it is only rotating about this point, which then means that I can show the tangential acceleration in this way. From the center of mass, I have my tangential acceleration this way, and then I have my centripetal acceleration in this way, wherein the value of the acceleration, tangential acceleration is L by 2 theta double dot, and as a force it will be ml. by 2 theta double dot. The centripetal one would be L by 2 theta dot squared, and I have M featuring there. Okay, so much completes the kinetic diagram. And then I have the free body diagram, where now I have to account for all of the restoring moments. In this case, restoring moment here would be related to theta dot as ct theta dot in the opposite direction. Let me allow myself to draw that out now. So I have ct theta dot acting in this way. It's a moment. So I show it with this curved arrow as ct theta dot. I have reaction forces that I must not forget. So this here is Ry, the some component Rx. Okay. Um, this spring, as it comes down, it would be in tension. So I have the spring in tension, and from this point, the reaction force would be upward. So show that here. What is the magnitude of this force? It would be K1 times how much does this end of the spring move down as it rotates by some small theta? It would be the arc length, that is L by 2 theta. Okay, this spring here is now related between this mass and this, so I do have to take into account some assumption. So let me write that down. If, let's say that, so for spring 2, let's say that this y is more than how much this moves. So let's say if y greater than, how much does this move? It would be the arc length again. So it's L theta. Then Fs2 is in, so essentially this has moved more than this, so it's in tension. With Fs2 is equal to K2 times y minus L theta. So that means then that this spring is in tension, and the reaction of that on this one would be downward, and on this one would be upward. Okay. Now, what about this spring? As this moves down for positive y, this spring would be in compression. So in compression, the spring is experiencing forces in this way, and the reaction on this would be upward. So I have this here is upward of, well, I'm directly writing it down as K3 times y. And similarly, if y dot is positive downward, then this would be in compression, and the resulting reaction would be C y dot. Okay, so I've gotten all of those passive elements, passive being simply that they aren't creating forces on their own, they're only restoring. Okay, so there's no energy that it is it's not using any energy, so all of these are passive elements. Not sure if I explained that before. Active elements would be such that it can create force and moment based on energy that's applied to it. We're not talking about that in this class. Okay. So we have all of those accounted for. So we have this one, this one, this one, this, and this accounted for. Now we have to remember always to check for the external forces and moments. So here we have um, F of t, and I have tau of t. Okay. So with this now, I can write down what is the equation of motion. We will have two of them, for one for theta and one for y. I'll try to be careful. Where should we take our moment about? We take it about this point. I'm going to name that as O. It's actually already named. It's hinged at O here. So I'm thinking about that so that the reaction forces vanish. And I'm going to do it with, let's say this direction is positive, and I'm doing it for the bar first. So starting with the free body diagram, we have first the moment ct theta dot minus tau of t. Then we account for the forces. So these forces have zero moment. This one is at a distance, well, the line of action is at a distance of L by 2 cos theta, because we have theta defined in this way. This here is theta. So K1 L by 2 theta is the force, and then this here is L by 2 cos theta. Is it positive or negative? R cross F is in the same direction, so it's positive. And then you have this one as well. So it is K2 y minus L theta. What is the moment arm length? It is L cos theta. And is it positive or negative? It is R cross F. It's in this direction, that is opposed. It's minus. Accounting for this, this, and this, and this. So we have everything in the free body diagram. Now for the kinetic diagram, I now have this as ml squared by 12, which is in the opposite direction. So minus ml squared by 12 theta double dot. And then this has 0 moment arm length. This one has L by 2 moment arm length. So L by 2 ml by 2 theta double dot. The positive or negative, R cross F. It's in this way. It's negative. So I could rearrange this, or I'm just going to say that for small theta, I will have this simplified or linearized as ct theta dot minus tau of t plus k1 L square by 4. Cos theta is close to 1. It's just L square by 4 theta minus k2 y minus L theta times L. Again, cos theta becomes 1, it's very small, is equal to And I have here, I'm just going to simplify this, and I will get ml squared by 3 theta double dot minus one. So now if I want to write it in a standard form, I will have it in decreasing order of derivatives. So theta double dot plus ct theta dot plus, I collect the theta terms, and I will have k1 by 4 plus k2 L square collected with theta minus, I have k2 Ly is equal to tau of t. Okay. Now for the mass, here do we take moment? No, it's sufficient to just take the sum of forces in the free body diagram. What direction do you want it to be positive? I'll say downwards. Because there's digital for me, I'm just going to copy this so it's visible for me. Okay, now what are the sum of forces? In the free body diagram, you have downwards only f of t, upwards you have c y dot k3y k2 y k2 l theta. I just broke this up so that I have it easier to rearrange, is equal to m y double dot. And if I now rearrange it, I have my double dot. I have this k2 plus k3 and then c. So plus c y dot plus k2 plus k3 y minus k2 l theta is equal to f of t. These are my two equations of motion. What this means is, if you have the initial conditions, which is initial theta dot, initial y dot, and you know what is your input tau of t and f of t, your model will allow you to then define how the system will behave as time evolves. Okay, that's the whole reason why we're doing all of this. We haven't yet gotten to the part where we can predict or we can define how, an explicit way of writing y of t is equal to something and theta of t is equal to something. Instead, right now we are defining the system models. So this is one representation that will be familiar to someone if you were to hand them this as your model. But we are also looking at state space representations now. So try and write this in your state space representation. How would you do that? Well, first you want to isolate your theta double dot. I will now divide everything by ml squared by 3, which gives me this 3 by ml squared. You have k2 ly minus k1 by 4 plus k2 times l squared theta minus ct theta dot plus tau of t. So this here is writing the differentiation of theta dot. Then I have d dt of theta is equal to theta dot. Then the next thing I have is y double dot is equal to, now to differentiate, you divide everything by m, so you have 1 over m, and then you have minus cy dot minus k2 plus k3 times y plus k2l theta. Don't forget, you also have f of t. This here is essentially the differentiation of y dot. So this here is d over dt of y dot, and then you have d dt of y is equal to y dot. So these are the equations that we have to now have in our state space representation in that linear form with matrices. As you can see, these are all first order, right? That's why it's now 4 first order equations for 2 uh, second order equations, ODEs. So previously, I think I had written it in this way. I have d over dt of some, say, vector. Instead of this, I could also do just theta dot and theta dot. That's also fine. Okay, so both of them are fine. In this case, I don't want to keep writing d dt, so I'm just going to write the differentiated form of the state vector. So I want to give myself enough space to do this because I see that there are many state vectors, state variables. Now, this here is on the left-hand side as x dot. We need to have x in the same order. Now you want to give space for that matrix. Plus, now, how many inputs does this system have? You have tau of t and f of t. So they're going to feature in your input vector. So, of course, the number of rows will be the same, but you have now 2 columns. And here you have tau of t and f of t. So when I now do this, I want to make sure I don't go into, I want to make it clear. That's why I'm drawing these guidelines. Okay, we're just going to carefully write down what are the coefficients of each. So in this case, we have for y, you have 3k2l by ml square. So that will come in this position here. So 3k2l, no, l is divided, so 3k2 by ml. That's the first term. Now the second term is for theta. So that comes over here. So you have minus of k1 by 4 plus k2 times this L square cancels out, and then you have 3 by m. Then you have for theta dot, you have minus 3 ct over ml squared. And you don't have anything with y dot, so it's a 0 there. You have, in terms of the input, you have 3 by ml squared times tau of t. You don't have anything to do with f of t, so it's a 0 there. The second one is the differentiation of this is equal to theta dot. So it's this line here. It's just saying this is telling you what that second variable is. There's no relation to tau of t and f of t. Y double dot is equal to, in terms of y dot, it is minus c by m. So minus c by m. In terms of y, you have minus k2 plus k3 over m. In terms of theta, you have k2l by m. And theta dot does not feature, so it's a 0 there. Tau of t does not feature, and so you have 0 there. F of t has 1 over m. And finally, you have 0, 0, 1, 0, and 0, 0 here. So this here is x dot, this here is a, x, b, u, giving you x dot is equal to ax plus bu form. Okay. I hope this is clear. We have touched upon a few extensions of ideas that we've been discussing, and we've written it in the state space form.